The second speaker is going to be Sebastian. Are you here, Sebastian? Okay, I cannot see Sebastian in the cannot see Sebastian. Maybe your name. Okay, yes, I'm on the line. Okay. Let's wait a second, and we can enable you as a. Okay. We couldn't find you, Sebastian, because to us your name was unknown user. So, but now, okay. Okay, now I think you can.
Hello.
Okay, okay. Hi, Sebastian.
Great.
So,
hello.
just a brief introduction. So, Sebastian Grijalva is from Pasqal. He's a quantum software engineer at Pasqal. And today he's going to talk about their quantum device, the quantum processor. This is a neutral atom quantum processor. He's going to talk, he's going to explain us how to program their device and something about applications and the emulation of this device. This is an important thing to take in mind. So please, Sebastian, go ahead.
Thank you, Ricardo, and to the organizers at Cinica for this nice workshop. This morning, I would like to speak a bit about what we do at Pasqal and to discuss some of the updates we have on the applications and emulation side. As you know, Pasqal is a startup. We're a 2-year-old startup that is building neutral atom quantum processors. So these experiments began at the Institut d'Optique at Palaiseau, France, and it was originally an experimental laboratory by Antoine Bourreis and Thierry Laïc, which was dedicated to controlling atomic matter and with the expectation that to eventually move into information processing. Eventually, there was a spin-out, which is Pasqal, and who is now trying to build the processors. As you see here, this is one of the actual prototypes now, which are based on neutral atoms. So the qubits themselves are these atoms, for example, rubidium, which are trapped in optical tweezers. So as you can see here, you have several atomic traps, and each one of these green dots represents an atom, which is guided to move between two electronic levels. It's a Rydberg atom. So this is a particularly scalable technology. You can have hundreds of these atoms in these traps in arbitrary 2D or 3D geometries, as you can see in the picture. As I said, the electronic states of these atoms, the electron is storing the quantum information. So this can be seen as a qubit. The interactions then happen because of the dipole-dipole force that exists between these Rydberg atoms. So there is a large connectivity inherent in these types of systems. Now, these neutral atoms, besides their potential for many body quantum physics, they are one of the most useful quantum simulators, which means that they can be used to extract information from a quantum system with another quantum system. But besides that, many body quantum physics applications, they can also they hold the promise to be useful for chemistry and then for drug discovery and also for high energy physics. This has been used in several experimental research papers. But it can be also used in hard computational problems. For example, in this case, you see a set of maximal independent sets So imagine that if the atoms that I showed in the previous picture were either in its excited or ground state, and if this corresponded to a red or white dot, then some of these points would correspond to subsets of a graph that are not connected by a link. So these types of problems are natural for the system that is described by the neutral atoms. They can be used, for example, for approximate optimization, and also for quantum enhanced machine learning. If you try, for example, to characterize the different graphs that are formed with these atoms. Now, from the point of view of numerical simulation in Pascal, we are beginning to attack several interesting issues that arise in the developing of these applications. We can discuss two main features: the few atom emulation, which is based on fundamental testing, studying noise effects, and the design of digital quantum gates. I will precise later how exactly these are built. And then there's also the large atom arrays, in which we are interested in understanding the behavior of quantum algorithms for large arrays, as I said, for graph or combinatorial purposes. And finally, there's the need for quantum-inspired solutions, so optimal control, measurement estimation, and tensor network simulations. So with respect to few atom emulation, I will go into a bit of detail. These transitions, as I said, between a ground and excited or Rydberg state are actually a more complicated two-photon process. So this is it's guided by two lasers, each one driving the atom from an initial state to an intermediate state and then to the desired state, the Rydberg level, and which is subject to imperfections. For example, state preparation and measurement errors. You can have a spontaneous emission from this intermediate level. As you see, there's here another so-called garbage state. You can have Doppler effects induced by the finite temperature of the atoms and the way that the lasers act on during the transition. And of course, you have the imperfections in the laser noise. So one of the goals of the emulation team in Pascal is precisely to have a model of these types of interactions. These effects, these noise effects, can be, for example, witnessed when doing a pulse sequence. As, for example, the simplest one would be to find the Rabi oscillations between these two levels, 0 and 1, and then we extract a model of the noise. There are several techniques for doing, which come from from first principles to try to add all of these effects into a big model. There could also be a machine learning model that is learning how these different errors appear. And then whatever the model is, you use this for design and testing of new features. So this, for example, is in red is the results of a model, and then the line is the results of the model, and the dots represent experimental data. Now, the noisy emulation is used to verify and plan the behavior of the pulse sequences that we constitute, for example, quantum algorithms. Here, for example, you see real experimental results in blue from a particular pulse sequence that is a part of an algorithm, and then you have to match it up with the noisy results. So in Pascal, we have developed this first noise model, and now we are collaborating, for example, with Gieneka in order to find different types of approaches to finding these errors, which are expressed as, for example, in the case of spam errors, these are probabilities of having, one of the spins, or in this case, the qubits, sorry, flip to a 1 instead of a 0, or a 0 instead of a 1. These are probabilities. And you also have a standard deviation on the laser properties. This can be also used in the case of digital quantum gates. So just to explain a bit the principle behind digital gates in neutral atom devices, the first step is to put your atoms into two hyperfine states. So these are states which are not Rydberg or very excited states. These are just close to the lower energy level states of the atom. You pick two of them and you call them ground and ground 0 and ground 1, if you wish. So this will be your digital basis. And then you use the Rydberg level, this highly excited energy level, as a way of introducing interactions between the atoms. So this is no longer guided by lasers, but this is actually guided by what I call the dipole-dipole interactions of the atoms. So here you have a sequence of 3 steps, which are each one corresponds to a rotation, if you wish, of the qubit in the Bloch sphere, which will make the atom go into the Rydberg level. The first one, I called it a pi pulse because it corresponds to a rotation of pi in the Bloch sphere. Then you have a second one, which is the target. Depending on the value of the control, we expect the target to have a different effect. And when it's trying to reach the Rydberg level, then there's this shifting of the energy caused by the dipole-dipole interaction. So basically, the Rydberg level is used as a way of introducing this quantum logic between the qubits. And then, when we are done, we will relax the atom back to the digital basis. So by beginning, for example, here in 0, 0, we end up with a state which has gained a phase because of this rotation of 2 pi. And this is the protocol for all the different combinations of the control and target qubits. This is the protocol for a control Z gate. And from then on, we can build the control NOT gate by using local action, using what is called a Hadamard gate, which is another rotation that we do on the digital basis. But in order to do all of these steps, we have to go back to the 2-photon process and then to the transitions between these ground and hyperfine ground states, which is then what is called a Raman transition. So we are using beginning a model of this that is based on Julia, and we are using this to be as detailed as possible. And as I said, also there's the machine learning approach. Now, when you have when you're satisfied with these transitions, you go into an intermediate level, if you wish, which is called the pulse sequence design level. So for this, Pasqal has devoted some effort into developing an open source project, which is called Pulsar. So this helps you designing the pulse sequences for a neutral atom device. So here I set up an animation of what Pulsar looks like. You can basically design all of the channels that act on your register. So imagine here are your atoms, and then you include the instructions for each of the channels. Some of these channels are local. They act on specific atoms. Some of them will be global. So they act on the entire register. This is going to be the first version out. We are now developing the graphical user interface so that it becomes more easy for pedagogical purposes. Although one of the main objectives of Pulsar is that it allows you to send instructions to an actual quantum processing unit, for example, those that are built by Pasqal, or that is capable of being emulated efficiently. So this is a representation which is in a lower level than the circuit representation, although you could abstract things into quantum gates and then compile them into pulse sequences. So for example, many of the projects that we are doing with Cinica, they used this representation to try to, for example, to find optimal pulse sequences for specific purposes. The original backend was a project that was done with the Unitary Fund and QTIP, and which is based on leveraging on all of the open source packages that are used for simulating quantum systems, which goes from SciPy, then QTIP, and then Pulsar, in order to run these simulations. Everything is open source, and you can access the code, and you can simply run pip install Pulsar, and then you can begin playing with the tutorials that we have put online. Now, associated to all of these simulations, there is what we call the quantum associated or quantum inspired algorithms. And there are many tasks that are related to the actual running of a quantum algorithm. For example, if you have pulses at your disposal, then you might be asking, what is the best way of applying them? What is the best pulse shaping techniques? How can I introduce a good cost function and a good optimizer function that allows me to defeat any variant plateaus or noise, or actually to avoid them? And so this is what is called the quantum optimal control in general. Now we can also leverage on one of the important points of the neutral atom architecture, and that is the freedom that you have in the connectivity of these atoms. So we are not bound to any underlying lattice or any particular positions. So we can choose the connectivity that we want in our system, and you leverage that to, for example, tackle QAUA problems or even to solve quadratic or constrained binary optimization problems, these Kubo problems. You can use the freedom in the embedding of the system to solve approximately and with good success on many of these problems. One of the goals of the emulation team in Pasqal is also to study ways of efficiently simulating the system in these types of problems in small sizes, so that everything is under control, and then verifying it with the machine, just as with the histograms that I showed you some minutes before. For example, truncating the Hilbert space to certain types of transitions, and then studying graphs, particular graphs that are formed under these pulse sequences. So here is, for example, an example of some embedding that it represents a Kubo problem. In this case, it was a 10 by 10 Kubo problem, but this can grow, as you see, to what is the current capabilities of Pasqal, which is 100 atoms. And then we can also use some of the quantum machine learning applications, which is the implementation of a quantum evolution kernel. For example, if you want to classify graphs that are formed with these atoms, you can use some sort of pulse sequence to understand how these graphs behave under the sequence, and then try to find correlations between them. Finally, for the measurement of these systems, we have what is called a projective measurement. So we either see zeros and ones for the Z basis. So this means that we should find clever ways of optimizing the number of shots that we take. Because if, for example, you want to do a tomography of the system, you will need a lot of resources. This takes us to the study of classical shadows and de-randomization for intermediate scale applications. For example, a BQE algorithm, which uses de-randomization and the fact that you can actually do these rotations locally on each of the atoms to choose each of the observables of the molecular Hamiltonian, and then use this to reduce the budget of shots that you require in your system. So the next steps will be for large array simulation. These are examples of hundreds of neutral atoms that are in square or triangular lattice that we produce at Pasqal. But in order to understand better how they behave, we need to have simulation of these. For example, if one was interested in building a particular type of state, preparing a state. One of the ways that you can follow this as your size grows is to use tensor networks, a matrix product state representation. That's the technical name of what you use in a zigzag form, and then to try to understand how the correlation function behaves for these types of systems. Of course, there are many other approaches if you change the geometry, but it's an interesting research and also application problem to understand how the large arrays of qubits behave. Especially because when some company or some group announces that they have some advantage or some supremacy, as in the case of Google, there are many other groups that are trying to put this into test. And some of the main ways of doing this adversarial benchmarking is to try to use tensor network algorithms. Now, as a summary, I guess you could see that the numerical computations in Pasqal depend on the number of qubits you're interested in. So you have a few qubits, you can still do a lot in terms of understanding the fidelities and the errors that are happening in your machine. So it takes a lot of computation in that side. Atomic physics level emulation, and we are working hard in trying to have the most detailed model possible to help with the hardware design. As you grow the number of qubits, you can start designing your pulse sequences. As I said, this idea of using pulsar to design pulse sequences to shape the pulses, the laser pulses that act on the system, and then try to use some packages, so either SciPy or even some lower level code such as C++, based on state vector evolution. Once you go past the very, I don't know, 16 or 20 or 20 atoms, you are with the problem of having a large array of atoms. So in order to extract some information, you will need tensor networks, and especially as you see in many places, this is the point in which you start needing a large cluster, for example, the GPU backend, or even something larger as the supercomputers that are offered by Jenica. So with respect to GPU at Pasqal, we have begun a collaboration with NVIDIA, and we have acquired a cluster of the latest DGX A100. This is designed for powering research and development at our company. And we are also using it to research application interactions. Maybe there's some cases in which some applications require a hybrid model, not necessarily just a completely quantum approach, but there is some interaction. For example, in the case of quantum machine learning, also in the case in which you need to optimize parameters in some clever way. And also because Pasqal is interested, in the HPC ecosystem, into interact with all of the different tools that are in this high performance computing. So we have acquired these cluster facilities, these GPU clusters, and we will begin developing from January of next year in the tools provided by NVIDIA. Precisely to do the different tasks that I mentioned during this talk. So to finish this short overview of what we're trying with numerical simulations in Pasqal, here's a bit of the roadmap of our stack. So the Pasqal QPU, we're not seeing it, as an isolated tool that is solving problems by itself alone, but it's part of a roadmap of development. So on top, you may have the applications, the exact, the precise SDKs that allows you to solve different problems, QUBOs, I don't know, quantum chemistry applications, differential equations, nonlinear. But then we also want to understand how to best design the way that these applications are being performed on a particular type of processor like ours, which is neutral atoms. So this takes just beyond design. Also, there's some compiling between the quantum circuit representation to something that can be performed in the hardware. And then we have this other side, which is based on emulation, which for the moment was just a module in Pulsar, but is now becoming our efforts in understanding what classical computing can give to quantum computing in terms of understanding, and vice versa, what quantum computing teaches us about what classical computers can do. And beyond that, there's the idea of using BDS tools like quantum, but also to create some customized tools, code for this liquid architecture. And finally, in the bottom, we might have some cluster of GPUs, or maybe using a supercomputer like those offered by Jenica, like Marconi 100, or even the new projects that they have ongoing. So this was this concludes my presentation. You can ask me any questions about what happened, but I would like to thank you for the opportunity of showing us what we're doing at Pasqal. Thank you.
Thank you very much, Sebastian, for this great introduction. So let's see if we have some questions. I think you can, if you raise your hand, I would like to recall, you can ask directly the question. Okay, see one question in the chat. Can you explain again why is it possible to reduce the number of short pulses with rotation of atoms? Are you increasing the number of qubits?
Okay, so this is what is called the de-randomization technique. So the idea is that if you, for example, try to measure an observable, a list of observables, so you have a Hamiltonian with many local terms, I don't know, 10 or 100 or hundreds in the case of quantum chemistry, you need to calculate the expectation value of each one. And that's very costly in terms of the number of shots that you need. So what you do is to use some statistical, some estimator of these observables. And there is a result that was done by the group of Pasqal and I forgot the other names, but it was the group of John Pasqal, in which they studied how to obtain how to predict all of the observables at once. For this, you need actually a logarithmic number of measurements in the number of observables. So if you have 100 observables to measure, you actually need 10, a factor of 10. And then, of course, it increases with the positions that you want. So this is based on the idea of using randomized measurements. So instead of measuring the exact list of observables, you used randomized Pauli strings. And you can even go further and actually de-randomize them in such a way that your confidence bound, so the thing that tells you that you will achieve a certain precision, in such a way that this value is optimized. So you see there's this idea of using randomized measurements with local rotation on each qubit, and then de-randomizing it in order to obtain the best possible sequence of measurements that give you the best information possible of your list of observables.
Thank you. Okay, let me just ask you one question. So, like, what's your vision about the integration of the Pasqal QPU with an HPC system? So what do you think are going to be the best way to integrate them, or the best algorithms in the future?
I think that there is many connections now with machine learning at the moment. There is not a clear picture of what exactly the place of a QPU is, but we are seeing that, for example, if you're trying to use some classification task, there's a component of the quantum processor that is useful, but by no means it can work in isolation. So there is necessary some aspect of communication between a GPU facility or even a supercomputer, because the QPU is very specific in the task that it does. So we need to learn how to program with this in mind. How to build a full stack in which we understand what is the precise task that the QPU will perform and what is the type of data that it will receive. There is quantum data in the sense that if you want to prepare a graph with the atoms, so it takes some resources. But there is also just classical data in the sense that you can embed the information on them as you wish. And it's important for us to understand how to best relate these two worlds. The vision is that in the future, the Pasqal or a quantum processor is just a part of a huge computing center for the moment. So it's that is the approach that we're taking at Pasqal.
Okay, yeah. Thank you so much. I think that's it for the moment. Yeah. And so thank you again, Sebastian, for being here. Thank you for your contribution. It's always a pleasure to have you, people from Pasqal, here at our conference. So I think we have the break right now. So we're gonna see again each other in 15 minutes. So at 11:15.
Okay. Thank you, guys. See you in 15 minutes.